So far, we've been talking about simple linear regression, where the word simple corresponds to that we only have one independent variable. But you can have regression models with more than one independent variable. In that case, we are dealing with what's called multiple linear regression. So this little subsection here describes how one could work with multiple linear regression models. Here's one example of a model. Expected value of y is equal to beta 0 plus beta 1 times x1 plus beta 2 times x2. So we have two separate independent variables now. Now the interpretation of x1 in this model is much as we defined at the very beginning of this section, and that is the expected value of y will increase by beta 1 for every 1 unit increase in x1. But we have to add a little bit of extra stuff to this now that we have more than one independent variable in our model. We have to add to it holding x1 constant. And the reason being is because we can't have this x2 changing while we're looking at a change of 1 unit in x1, because x2 obviously can also affect the expected value of y as well. Now you can make a similar interpretation then for x2 as well. The expected value of y will increase by beta 2 for every 1 unit increase in x2, holding x1 constant. Now, how do we get more than one independent variable into our model when we use the LM function to estimate the corresponding statistics, beta hat 0, beta hat 1, beta hat 2? Excuse me. The way that you can get multiple independent variables into your model is in the formula argument, where you would say y tilde x. Now we have x1. Now you say plus x2. This doesn't mean that you're adding x1 to x2. Rather, it means basically the word and. I want to include x1 and x2 in our model. So that's the syntax in R to do this. Now, sometimes there are transformations of the independent variables that are useful. So, for example, let's consider we had a scatter plot that looks like this, where we can see that indeed we have a trend, but it's not a linear trend. It's like a quadratic trend. And so if I were to put a line between the middle of the points, you can see we have this quadratic trend here in our model. Well, to account for that, what we might want to do is look at a model such as this. Expected value of y is equal to beta 0 plus beta 1 times x plus beta 2 times x squared. So that squared part there is what's going to capture that curvature that we see in that scatter plot. How can we tell R that we want to look at a model with x squared in it? Well, it's very simple. Here's our formula argument in LM again, y tilde x, and then we have another term, let's say, to our model. So we put plus in there for and. And then, as you might expect, we use x caret sine 2. But we also need to enclose all that within the I function. And basically what that tells R is that treat this x caret 2 as what we really mean, which is x squared. Now you might be thinking, well, why wouldn't R think it's x squared anyway to begin with? The reason why will be clear at the end of this page here. But we definitely need to put the I function there, surround that around that x squared. Now there also may be situations where you want to include what's called an interaction in one of these models. So let's say we have a model with x1, we have a model with x2, and what an interaction is simply x1 times x2. And basically what that is trying to capture is the fact that as x1 has, let's say, an effect, and that should be a capital Y there, as x1 has an effect on the expected value of y, look at this. It also has another effect that depends upon what x2 is. So if, let's say, x2 was 1, now we have beta 3 times x1. That's going to have a different effect than, let's say, if x2 is equal to, let's say, 10. now we would have a beta 3 times 10 times x1 there instead. And so how x1 affects the expected value of y is a function of of x2, its level. Similarly, how x2 affects the expected value of y is dependent upon what level you're at for x1. And so that's what an interaction kind of model looks like. How do I tell R that I want an interaction model, or model with an interaction? There are 3 different ways. Formula equal y tilde, x1 plus x2 is like what we've seen before, plus x1 colon x2. That does the x1 times x2 part. And again, you might be thinking to yourself, well, why don't we just put like x1 asterisk x2? Well, you could do that. The way that R interprets that, though, is essentially you want x1 in your model, you want x2 in your model, and you want this third part there for x1 times x2. So both can be used, but you have to understand the syntax in terms of what it's representing. One last way to include the interaction is this. Use parentheses x1 plus x2, and then at the end of the parentheses, caret sign 2. And what that is saying is that you want x1, you want x2, but now you want to look at the pairwise interactions, or the two-way interactions, to multiply x1 times x2. And so because of how R treats this caret sign 2 there, that's why then we needed to use the I function up here when we wanted a quadratic term in our model. Okay. Also in our model, now this is on page 3, we can include what are called qualitative independent variables. What that means is these are independent variables where they're categorical in nature, such as gender, such as, let's say, political party affiliation, where one level of those categories there is not necessarily, let's say, greater than another level of some other category. So we have qualitative or categorical variables. Here's an example of how to include this in a model. So let's consider gender as an independent variable. And here we're just going to use the traditional definition of gender, where we have male and female. And so what we can do to get gender into a regression model as a variable, let x equal, let's say, 1 for female, 0 for male. So notice it took one variable here to get a 2-level qualitative variable represented by a variable in our model. This 0-1 coding here, you'll see this a lot when we're dealing with qualitative variables. This is what's referred to as an indicator variable, because it indicates which level of the qualitative variable you're talking about. So if I wanted to include then this x in my model, the expected value of y is equal to beta 0 plus beta 1 times x. So for males, which is x equals 0, notice how my model simplifies. The expected value of y is equal to just beta 0, because 1 times beta 1 is 0. If x is equal to 1 for female, the expected value of y is equal to beta 0 plus beta 1 times 1, or just simply beta 1. And so notice that here again, we have one independent variable here. And due to that one independent variable, we have a unique coding in our model, unique representation in our model for both male and for female. Now also, think of it this way. So the expected value of y for male. So this is like, what would you expect the average for the males for whatever you're measuring? Maybe it's GPAs, for example. What would you expect that to be on average? So we could call that, let's say, mu. How about mu sub m for male? Similarly for females, mu sub f. And we might be very interested in making a comparison like this, similar to what we've done earlier in this course. Mu f minus mu m, is that equal to 0? Actually do a hypothesis test corresponding to that. If it is equal to 0, it means that they're equal. Well, notice though what this is equivalent to now with respect to a regression model. If beta 1 is equal to 0, then the male mean is equal to the female mean. So thus, if I were to do a hypothesis test where HO is mu f minus mu m is equal to 0, that is essentially equivalent to doing a hypothesis test for beta 1 is equal to 0, now represented here in a regression sense. Let's take this a step further. Let's compare this to now using ANOVA models in a completely randomized design. So hopefully you remember us using an ANOVA model such as this. The expected value of y is equal to mu plus alpha sub I for, let's say we have just two levels of our factor, level 1, level 2. This was what was called a treatment effect model, where mu was, let's say, some overall mean. Alpha sub I was then the deviation from that overall mean to represent the treatment or the factor level effect. Well, in this particular setting, if you remember, we let alpha 1 be equal to 0. And so what that means is then that for level 1, the expected value of y is equal to mu. The expected value of y is equal to mu plus alpha 2 for factor level 2. Notice how that's basically exactly the same as our regression model that we were looking at for males and for females. Just we have a mu and an alpha versus a beta 0, beta 1. But it's the same. So this then shows us how a regression model with one qualitative variable is equivalent to a one-factor ANOVA model. A very, very, very important idea to grasp in this class, and especially if you do work in statistics outside of this. Again, essentially an ANOVA model is a regression model when you are working with qualitative variables in a regression model setting. Very important. Now you might be wondering, well, will anything change with my regression model if I set x equal to 1, x be equal to 1 for male now and 0 for female? Will anything change with it? Well, your estimates for beta 0 and beta 1 will change, but in terms of your inferences that you make, they will not change at all. And so that's obviously a good thing to have. Well, let's look at a situation where, let's say that we have a 3-level qualitative variable and we want to include that into a regression model. Such as if we look at political party affiliation, let's say Republican, Democrat, and let's say there's just one other level, we'll call it independent. Then what we can do is we can now form 2 indicator variables to represent the 3-level qualitative variable. Before we had a 2-level qualitative variable, and we only needed 1 indicator variable with it. So what we can do is, let's say, create a variable called x1. It's going to be a 1 for Republican, 0 otherwise, meaning Democrat or independent. We're going to have a x2 be 1 for Democrat, 0 otherwise, so Republican, independent. And so that if we were to write out a table of how we're doing this coding with these indicator variables, this is what our table would look like. X1 is 1 for Republican, 0 otherwise. X2 is 1 for Democrat, and then, if I can kind of circle that, 0 otherwise. Let's represent this now in our model. So perhaps we are, let's say, Y could be, it could be GPA, maybe it could be income level. It could be lots of different things. And what we want to do is look at the expected value of Y, essentially as a function of political party affiliation. So we would have our model beta 0 plus beta 1 times x1 plus beta 2 times x2. And in terms of now when we fill in what x1 and x2 are by Republican, Democrat, or Independent, look what happens. For Republicans, we have beta 0 plus beta 1. For Democrats, we have beta 0 plus beta 2. And for Independents, we just have beta 0. But the key is each level of that qualitative variable has a unique coding representation in our model. That's why we only needed 2 of these indicator variables to represent a 3-level qualitative variable in our model. And in fact, if you had, let's say, in general, let's say a C-level qualitative variable, you could do the same thing where now you have C minus 1 indicator variables. That's how you would represent it in a regression model. Well, let's compare this now to an ANOVA model for one factor. Let's say we have 3 factor levels. We could write out the model in terms of a treatment effects model, mu plus alpha sub I. This model here would allow us to do hypothesis testing, such as is the mean for Republicans equal to the mean for Democrats is equal to the mean for Independents? Are there no hypothesis? The alternative hypothesis, at least 2 means are unequal. We would construct like an ANOVA table, do an F, we actually call it F observed, sorry about that. Find this F observed test statistic, maybe form a p-value, and so on. We would do a hypothesis test for equality of means. Equivalently, in this regression representation of our model, all we need to do is do a hypothesis test of beta 1 is equal to beta 2 is equal to 0. That would be equivalent. If we come back up here, here's beta 1, here's beta 2. Look what happens if that's 0. Excuse me. Look what happens if that is 0. Well, the models now become exactly the same. And so that's why doing a test of these betas is equivalent. Now, we haven't talked about all the details about how to do this in a regression setting, but it's essentially exactly the same. There's actually an F test statistic that will allow you to do that. Okay, so let's take a look at an example. This is going back to our Wheaties example that we've seen earlier. So I read in my data as before, and if we notice, if I draw lines here between the different design types, so our factor is design. We have 4 different design levels. That's our factor levels or our treatments, and we're looking at the number of boxes of cereal sold at a particular store. In the past, what we've done is we've used the AOV function with it, and when we summarize results from that, we get our ANOVA table. Now, we also saw previously that one could use the LM function with this. And the reason that we can is because of this equivalence between ANOVA models and regression models with qualitative variables. So before, what we've done, we used LM. We have our number of boxes sold, that was response. And then our explanatory variable, our independent variable, or our factor was design. And what this factor design does, again, it tells R to say, hey, I have numerical levels there, 1, 2, 3, and 4. Treat these levels as actually factor levels, meaning that 4 is not greater than 1. Otherwise, what would happen here with a regression model is a simple linear regression model would be estimated where there would be one independent variable for design with levels 1, 2, 3, 4, where 4 would be greater than 1. But by saying factor here, it says, okay, I have a 4-level qualitative variable that I'm working with here. And what ends up happening then, let me actually go here in my notes, excuse me for a second. This is on page 8. What ends up happening then is what R does, it then estimates in the end 3 betas corresponding to indicator variables for factor level 2, 3, 4, and then it also estimates the y-intercept, beta hat 0. And this was equivalent then to mu hat in the treatment effects model. Let me actually write that in there. This is beta hat 3, which will be equivalent to alpha hat 4 in our ANOVA model. Now, to understand a little bit further about how R makes this judgment regarding how it codes the indicator variables, we can use a function in R called contrast. And if we use that with then the factor version of these design type variable, what we see here is a table that's essentially exactly the same. Let me come back here. As what I was using before with political party affiliation. The only difference now is that we have a fourth level down here in that table. And some of the coding is a little bit different too. Come back. Okay, let me erase. And so what we have here is that this is basically what X1 is. X1 represents design 2. It's a 1 for design 2, 0 otherwise. X2 is equal to a 1 for design 3, 0 otherwise. And then finally, X3 is equal to a 1 for design 4, 0 otherwise. With this particular coding then, we can write out what our regression model would be based upon what our output is. And again, this is essentially the same as the ANOVA model, is just represented a little bit differently. And to further emphasize the point, what I decided to do was I'm going to actually create independent variables, x1, x2, and x3, that has this particular coding. So if you have your notes open, what you can do is take a look at page 7, where the first 2 observations correspond to design number 1. So in that particular case, x1 would be 0. The next 3 observations correspond to design number 2, and that's what x1 is representing, so x1 has to be a 1. The next 3 observations correspond to design 3, so we get zeros, and the last 2 observations is design type 4, so we have 0, 0. I do the same thing for x2, the same thing for x3. I then put x1, x2, x3 with the actual original Wheaties data set into a data frame, call it now Wheaties 2, and now I estimate then a multiple linear regression model where I have x1 plus x2 plus x3. My data is in Wheaties 2, and look at this. I get the exact same beta hats as I did before. Okay. Now, to go ahead and form the ANOVA table is a little bit more involved, but one could do that. You can take a look at my notes here. You know, if you could take, or this actually would be more covered in a lot more detail if you took a full semester of a regression class. Okay. So then that completes then this section. Just a little bit of a touch on multiple linear regression. If you find this stuff interesting, take a whole semester on regression analysis and you do a lot more stuff like this with a whole bunch of other interesting models.